Hey everybody, this is part two to the final 17A final review that I posted. I'm going to skip problem 8 because it's graphing and it might take a little while. So I'm going to get through the rest of the problems. And then when I have a minute, I'll come back and do the graphing problems from problem 8. So let's look at problem 9 here. So this is the Challenor 17A review that I posted. Challenor 17A final review part 2. Skipping problem 8, starting with problem 9. Problem 9 says the following. The volume of a cone of radius r and height h is v equal to 1/3 pi r squared h. That's the volume of a cone. Probably going to draw a cone here, but let's read the rest of the question. If the height is given by h equals 3r, and the radius of the cone is increasing at 2 inches per minute, the radius is increasing at 2 inches per minute means that dr dt is equal to 2. You don't really need the units here, but I'm going to write them. Inches per minute. Find the rate of change of the volume when r equals 6 inches. So we want to find dv dt when r is equal to 6 inches. This problem has been set up in such a way that you don't really have to draw the picture. Like if I was giving you this problem, I might have said something more. Oh, actually, this problem's interesting. This problem's a little different. Yeah. So I might have set it up more like, you've got your cone and stuff, and we know that the overall cone has maybe say like a radius of 10 inches and a height of 30 inches. And then we're asking you like maybe we're filling up the cone in such a way that the radius of the water, which is kind of a weird thing to say, such that this radius is increasing at 2 inches per minute. And they're asking how fast is the volume of the water in the cone changing when the radius is 6 inches. So you say, oh, well, then you say like the radius to the height is equal to the radius to the height. So then you exactly get the same relationship that h is equal to 3r. And then you can do the same sort of thing. But sometimes the setup isn't so like explicit giving you this. Often they're like, you've got a bigger cone with these dimensions, and then they're asking how the smaller cone with the same ratio of dimensions, right? The radius is, or the height is 3 times the radius in this case, would work out. So let's set it up. I want to point out this is atypical because usually when we're doing these kind of problems with volumes and cones, we are writing this whole equation in terms of the height. Whereas in this situation, since they're giving us how the radius is changing, we're going to write this whole thing in terms of the radius. So we're going to take our volume equation, 1/3 pi r squared h, and rewrite it as 1/3 pi times r squared times h, which is 3r. I would simplify this before taking in derivatives. So the 3's will cancel, and you're just going to get the volume equals pi times r cubed. Then we're going to differentiate both sides. And the thing to remember here is when you have these related rates types problems, we are differentiating with respect to t. So differentiate with respect to time. So when we take the derivative of v, we don't just get 1, we get dv dt. We take the derivative of r cubed or some stuff cubed, we don't just get 3r squared, we get 3 times your stuff squared times the derivative of your stuff. My computer is nervous. Okay, anyway. And then I think we have all the information we need. We know that dr dt is 2 inches per minute. I'm gonna write the 3 in front here. 3 pi times, actually I'm gonna play r first. So we know that r is 6 inches, so 6 inches squared. Again, you don't really need to write the units. I'm just writing them to show that you do get the correct units. And dr dt is 2 inches per minute. So multiplying this out, you get 6 squared, which is 36, times 2, which is 72, times 3, which is 216. So you get 216 pi, right, because there's a pi there as well, inches times inches times inches, and inches cubed per minute. Now, I don't think you needed to include any of the units until the very end, because we should have known that we're talking about how a volume is changing. It should be cubic inches in this case, or whatever your units are per unit. That's the whole problem. Let's move along. Let's keep my pages in order here. Problem 10. Find the absolute minimum and maximum values of the function f of x equal to 3x minus 4 over x squared plus 1 on the interval So absolute extrema is another way of saying that, where you get the max and the min on the interval from -2 to +2. So first step, find the critical values. So f prime of x, you have to use the quotient rule. It's the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. We're going to simplify this, so we're going to multiply the top and get 3x squared plus 3 minus the 2x times 3x is going to be 6x squared, and the 2x times -4 is going to be -8x, but it's minus the -8x, so it's really plus 8x, all divided by x squared plus 1 squared. Simplifying further, we get a -3x squared, right, because 3x squared minus 6x squared, and a plus 8x plus 3, all divided by x squared plus 1 squared. We're going to set that equal to 0. For these kind of problems, well, for this kind of problem, you actually shouldn't have a place where this function is undefined, because to have an absolute extrema on a closed interval, the function has to be continuous. But if we were looking for like just critical values, or to find where a function is increasing or decreasing, we would set this equal to 0 and also see where it's undefined. And places where it's undefined, where like you might have a vertical asymptote, you always have to include on your number line. Here, that's not an issue because x squared plus 1 is never equal to 0. It's always greater than or equal to 1. So we multiply both sides by x squared plus 1 squared, sorry, x squared plus 1 squared. You're going to end up just setting the numerator equal to 0. You get -3x squared plus 8x plus 3 equal to 0. We're going to factor this. I would probably do one thing and multiply both sides by -1 because I don't like factoring when my coefficient of x squared is negative. It's going to be easier to factor this. There's a couple ways to do this. There's not a lot of options here. In fact, there's really only kind of, so you could actually kind of use the method or you kind of guess and check. So here's what I know. I know if I'm going to factor this in the usual sort of quadratic factoring way, I'm going to have a 3x and an x. It's the only way to multiply to 3x squared, right? 3 is a prime number, so the factors have to be 3 and 1. Now, interestingly here, we're also stuck with a 3 over here, a -3. So it either can be -3 and 1 or +3 and -1. But here's an interesting point here. This original expression, you can't factor anything out. If we could have, we would have. But here's what that means. You can't put a 3 right there or a -3 because if you did, you could have factored out a 3 from this factor, but we know we can't factor anything out. So I'm going to put the 1 here and the 3 here. And let's see, I want to get a -8x. I want a -3 here so that 3x times -3 is -9x. And then a +1 here so that +1 times x is +x. And I can give me a -9x plus x, which is -8x. Set that equal to 0. And we get two critical values. We get x equal to +3 and we get x equal to -1/3. Now, this is a well-written problem in that the critical values, one of them we don't need to worry about because it's outside of the interval that we were given. So you only should consider critical values for this kind of problem that are in between the two values that are the endpoints of your interval. So here, after you find your critical values, we're now going to test all the CVs, the critical values, and the endpoints in the original function. So we're going to look at f of -1/3. We're going to look at f of -2. We're going to look at f of +2. Okay, f of -1/3 is a little bit annoying, but let's do it here. So we're going to get 3 times -1/3, which is -1 minus 4 over -1/3 squared plus 1. If I was designing this problem, I would have made it so this was the one that we didn't have, and this was the one that we did have, but I wasn't the one who wrote the problem. This is a good time so this would be a good time to double check to make sure I didn't make a mistake finding my critical values, because maybe the -1/3 is really not what I wanted. If I double check here though, it seems like it's right. Yeah, I'm pretty sure that's correct. Maybe he didn't mean for it to go that way. Let me double check. Let me double check my work here just to be absolutely sure. 3x minus 4 x plus 1. The bottom derivative of the top minus the top derivative of the bottom. All over the bottom squared. That ends up becoming a 3x squared plus 3 minus 6x squared plus 8x. Now it looks right on. And then 3x squared minus 6x squared is -3x squared plus 8x plus 3. And then minus. Yep, that seems right. Yep. I'm going to grab, so I'm just surprised because usually for problems like this, people try to make it so that it comes out relatively nice. So I'm going to graph it real quick. So in fact, let's all look at the graph together. So let's new share. Here, that. Look at this for a second. We look at Desmos here. If we look at our function 3x minus 4 over x squared plus 1. Let's see. Do I see a critical value at negative 1/3? Actually, no. That's because I did plus 2. Ha ha ha. Plus 1. Let's see. Yep, I see a critical value at negative 1/3 and at positive 3. So yeah, okay, fair enough. Yes. So sorry. Okay, new share. Apologies. Great. So we'll leave that there for a second. We'll do the other two. So f of negative 2 is going to be 3 times negative 2, so negative 6 minus 4 over negative 2 squared plus 1, which is negative 10 over 5, which is negative 2. Interesting. And f of positive 2 is going to be 6 minus 4, also over 5, which is going to be 2/5. All right, let's check this out. This is going to be, so actually, here's what I know. And let's add a little, I'm going to look at the question. This is going to be negative 1 minus 4, which is negative 5. And I'm going to have a 1/9 plus 1, which is 9/9. Now, the question said, no, it said find the absolute minimum and maximum values. If it said to find where the absolute minimum and maximum was, well, I know, oh, actually, I don't know. We have to finish this up. I thought this one was a negative for a second. I know that one's going to be the maximum because it's the only positive one. So I get negative 5 over 10/9. Flip and multiply, it's negative 5 times 9 over 10, which is negative 45 over 10, or negative 4.5. So it looks like this is the absolute minimum. This is the absolute maximum. So absolute minimum value is negative 4.5. Absolute maximum value is positive 2/5. I would point out that the absolute maximum occurs at x equal to 2. The absolute minimum occurs at x equal to -1. Definitely for these maximum minimum questions, make sure you answer the question correctly. Sometimes they ask you what the value is, which is what you get when you plug in the value into the function. When you plug in the x critical value into the function, sometimes they ask you where the absolute maximum minimum occurs, and that is the x coordinate itself. So just make sure you read those questions very carefully. Let's look at the problem 11. If a rectangle has its base on the x-axis and 2 vertices on the curve y equals e to the negative x squared. Okay, so let's draw a picture here. So we have a rectangle that has base on the x-axis and the 2 vertices, yeah, sure, I guess, on the curve y equals e to the negative x squared. Okay, so y equals e to the negative x squared. I don't really know exactly what it looks like. I do know it's an even function, and maybe it looks vaguely like this. Where this would be the point, so this is y equals e to the negative x squared. Oh, nice. This would be the point 0, 1. So we're imagining like our vertices like here and here. So we've got a rectangle looking like that. And if we call this point here on the graph, if we call that x, y, well then the height of our rectangle is y, and the base of our rectangle is twice x. Okay. So the rectangle has its base on the x-axis and 2 vertices on the curve, so that the rectangle has its largest possible area when the 2 vertices are at the points of inflection on the curve. Interesting question. Okay, so we are trying to, let's say that let's just come at it. We want to maximize the area, which is equal to 2xy. Okay, but then we're going to plug in that y has to be equal to e to the negative x squared. So we're trying to maximize. That's a slick question. Maximize area equal to 2x times e to the negative x squared. Okay, so I will point out that maximizing this means we're going to take the derivative, set it equal to 0, find the critical value, etc. I will also point out that to find the inflection points of y equal to e to the negative x squared, you would take the second derivative set equal to 0, right? So the first derivative would be e to the negative x squared times negative 2x. Oh, look, these things are virtually the same. The only difference is by a sign. This is negative 2x times e to the negative x squared. This is positive 2x times e to the negative x squared. But either way you do it, when you take the derivative of this and set it equal to 0, or the derivative of that and set it equal to 0, you're still going to end up getting the same critical value. So I would maybe, I mean, I feel like this is kind of an interesting question because like, well, how much work do they really want you to show? So I would, if I was trying to like, if I was trying to move on to other problems quickly, I might point out that something like note that the critical value of a of x equal to 2x e to the negative x squared will be the same as the critical value of the second derivative of y equal to e to the negative x squared as y prime is equal to negative 2x e to the negative x squared is equal to negative a of x. So whether you're taking the derivative of this and setting it equal to 0, or the derivative of that and setting it equal to 0, either way, you're setting a prime equal to 0 and getting the same critical value. Now, if you actually want to show the work, we could do it. So a prime of x is equal to, all right, so it's going to be the derivative of 2x times e to the negative x squared plus 2x times the derivative of e to the negative x squared, which is e to the negative x squared times negative 2x. Factor out an e to the negative x squared as well as a 2. So you're going to get 2 e to the negative x squared times 1 there and an x times the negative 2x there. Equal to 0. This never equals 0, right? E to the something is always positive. So you set that part equal to 0. So you're going to set 1 minus 2x squared equal to 0. You're going to get 1 equal to 2x squared, 1/2 equal to x squared, x equal to plus or minus the square root of 1/2, which is the same as plus or minus root 2 over 2. So that's your critical value that's going to maximize the area. And then in a similar way, you could say that y double prime, well, I don't even need to do the work, right? Y double prime is literally, sorry, the derivative of negative a of x, right? Y of prime is actually negative a of x. And so if we take the derivative of that, well, we just did it, right? The derivative of a of x was exactly that. So the derivative of negative a of x is going to be negative 2 e to the negative x squared times 1 minus 2x squared. Set that equal to 0 to find your inflection points, and you exactly get x equal to plus or minus root 2 over 2. It's a clever question. I kind of like that. Okay, moving on to number 12. A model for the concentration of antibiotic drug in the bloodstream T hours after administration is C of T, the concentration at time T, is 1/2 E, sorry, 1/2 T squared e to the negative 0.6 T. And that is the concentration of the drug after T hours. So you took a drug and then T hours later, this is the concentration. Oh, sorry, you can't see that. I am so sorry. Off screen, terrible. So the concentration of drug in the bloodstream after T hours after having taken the drug is 1/2 T squared e to the negative 0.6 T. Which is interesting. So, well, I guess that kind of makes sense. So right when you take it, the concentration is 0, right? C of 0 is 0 because we haven't really gotten to your system yet. Okay, this seems not impossible. At what time does the concentration have its largest value? Or in other words, find the value of T that maximizes concentration. It's really important to read these questions carefully, right? If we want to find the value of T, where the concentration has the largest value, that's what they're asking you to do. They want you to maximize CP. There's a second part of this question here, but let's focus on this first part. So take the derivative I would leave this 1/2 out in front. And then the derivative of t squared e to the negative 0.6t is going to be 2t e to the negative 0.6t. I'm just using the product rule plus t squared e to the stuff times the derivative of the stuff is times negative 0.6. For all these problems where you're trying to find critical values, it's really super important that you factor as much as possible. That's kind of the only way to solve these. So I'm going to factor out from each of these expressions here a t, and so one of the t's there, and an e to the negative 0.6t. If I factor that out, a t and e to the negative 0.6t, I'm left with 2 here, and a t to the first here, and a negative 0.6. So I'm either going to get t equal to 0, which is not very exciting. Probably not when the drug is going to be maximal in the system, right? Because you just took the drug and concentration is 0. Or we're going to get, let's see. So this equal to 0, 2 minus 0.6t equal to 0, 2 equal to 0.6t, 2 divided by 0.6 is equal to t. If I was trying to simplify this, I would multiply the top and bottom by 10 and say that's going to be 20 over 6, which is 10 over 3. So t equal to 10/3 hours, or in other words, 3 hours and 20 minutes. Now, we should check to see that this actually gives us a maximum, because maybe it gave you a minimum. So I would probably use the first derivative test. Okay, so here's actually where I should read the rest of the question. So the rest of the question says, determine how many inflection points there are and at what time they occur. So normally I probably wouldn't decide just to take the second derivative here to use the second derivative test, but since I know I have to take the second derivative to find the inflection points, I might as well use that second derivative up here to test whether I have a maximum or minimum. So eventually, once I find the second derivative, I'm gonna say, okay, great. C double prime of 10/3 hopefully is going to be something that is negative, right? Because if this equals a negative number, that means the function is concave down at 10/3, which means we have a maximum. So let's do the work for the second derivative, and then we'll come back and say that. Okay, and we'll actually find the number as well. So let's see here. So inflection. So yeah, the second part says, how many inflection points there are and at what times they occur. So we'll point out, although it's really super important to factor out when you're trying to find the critical values, you don't want it to be factored. Like I don't want to take the derivative of this really. I'd much do I? I can't maybe I'm like saying something, but it's kind of no, it's kind of terrible because I have to use the product rule anyway. So I would probably rewrite this, and actually I'm going to distribute the 2 here, say that my c prime of t 1/2 times 2 is just 1, so t e to the negative 0.6t. And 1/2 times negative 0.6 is negative 0.3. So minus 0.3 times t squared times e to the negative 0.6t. Okay, I'm going to do one thing. I'm going to factor out e to the negative 0.6t. You can kind of go either way here. Okay, that looks all right. So now for this, I'm going to use the product rule. The double prime of t is going to be the derivative of that, which is e to the negative 0.6t times negative 0.6 times all that left alone, plus e to the negative 0.6t times the derivative of all that, which is 1 minus 0.6t. Again, we're going to set it equal to 0 to find the critical values of the second derivative to find the potential inflection points. So then we're going to factor out, and I'm going to factor out an e to the negative 0.6t. I think that's kind of all I can factor out. So factoring out an e to the negative 0.6t, I'm left with, and then let's go ahead and distribute this negative 0.6 here. So it's going to be kind of gross. It's going to be negative 0.6t, and then 0.6 times 0.3 is 0.18, right? It's 60% of 30%, which is 18%. So it's a positive 0.18 t squared. And then we have plus 1 minus 0.6t. I was really hoping that this and this were going to cancel, but they don't. So let's see. So we've got blah. So I'll point out that this is never going to equal 0, right? Again, e to the anything is never 0. So we're really just setting this part equal to 0. Simplifying this, I'm going to get 0.18t squared minus 0.6 minus 0.6 is minus 1.2t plus 1 equal to 0. That looks terrible. So what I would do, yeah, they actually asked us to find the value. So looking back at the question and say, at what time do they occur? I'd probably multiply everything by 10 to try and solve this. So I'm going to say this is 18t squared minus 12. Oh, sorry, not by 10, by 100 actually. Except move the decimal over 1, 2 places. So minus 120t plus 100 equals 0. That seems terrible, James. Yeah, I can divide by 2. I could just use the quadratic formula, but it seems really terrible. But what I should do before I do any of this is point out that this is my second derivative. So if I plug in 10/3 to this part here, d double prime of 10/3 is actually equal to, let's see here. So this means 0.18 times 10/3 squared minus 1.2 times 10/3 plus 1. Oh, these numbers are not pretty. Yeah, 0.18 times 10/3 squared minus 1.2 times 10/3 plus 1 times e to the whatever. But e to the anything is always positive. So zooming in here for a second, sorry, this looks a little bit heinous. So, right, so yeah, I feel like you need to calculate this really. Yeah, this is gross. Sorry, this, so 0.18 is 18 over 100 times 10/3 squared, which is 100 over 9, minus 1.2 is 12 over 10 times 10/3 plus 1, all times e to the something. Yeah, e to the something. E to the, we don't care. So cancel, 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 cancel over 2. So we get 2 minus 4. Whew, I was worried there for a second. Plus 1 times e to the whatever. That's a negative number times a positive number, which is negative as desired. I was a little worried there for a second. So the second derivative at 10/3 is a negative number, which means it's definitely a relative maximum at that 10/3 value, as it should have been, right? Because the question said, find the value that maximizes C of t. So that number is t equal to 10/3 hours. Cool. All right. Back to the second question here, which is to find the inflection points. Setting this equal to 0 just seems like a terrible pain in the butt. If I really had to do it, I would divide everything by 2 to get 9t squared minus 60t plus 50 equal to 0. I really don't want to try to factor that because it just seems terrible. But I'm trying to in my head, as I said, that I don't want to do it. Yeah. Yeah. So here's what you could do. You could just say t equals the quadratic, like actually use the quadratic formula and get 60 plus or minus the square root of negative 60 squared is 3,600 minus 4 times a times c is 4 times 9 times 50. 4 times 9 times 50. 4 times 50 is 200 times 9 is 1,800. All divided by 2 times 9. And then I'll point out that both of these are real numbers, right? So you get t equal to 60 plus or minus a number that is less than 60 all over 18. So we have 2 inflection points. Because the sign is going to change at each of these, because when you have a quadratic thing, right, a quadratic thing like this parabola here that I've come up with, 0.18t squared minus 1.2t plus 1, looks something like this, where it crosses the x-axis twice, meaning this whole function goes from either being positive to negative to positive. I should say this whole second derivative goes from positive, negative, positive, or it might be the other way and go negative, positive, negative. Either way, the sign is changing both here and here. So we have two inflection points, one at t, both, or I should say at 60 plus root 1800 over 18 and 60 minus root 1800 over 18. The numbers on this problem are a little bit gross. I'm not gonna lie. This one's extra gnarly. So yeah. All right. Continuing on, problem 13. Let me get back in frame. Let me zoom up a little bit here. Problem 13. Find a formula for the general term of the sequence. And our sequence is -3. Actually, the first terms of our sequence are -3, 5/4, -7/9, 9/16, -11 over 25. Often, if almost everything's written as a fraction, it's good to write all the things as a fraction as -3 over 1. So looking at this, I see three pieces to deal with. I see the denominator, I see the numerator, and I see the alternating part here. So I'm going to think about this as a sub 1, this is a sub 2, a sub 3, a sub 4, a sub 5. So it looks like the denominator is just the square numbers. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. So the next number, at least the denominator, would be 36, right? That's going to be 6 squared. And the nth term would be n squared. The numerator, on the other hand, looks like it's just, if you ignore the alternating part, it looks like it's increasing by 2 every time. So I should point out the denominator, 1, 4, 9, 16, 25, is just n squared. The numerator, 3, ignoring the alternating part, 3, 5, 7, 9, 11, the next term will be 13. And if we try to find a pattern for this, well, again, we're taking, well, if we're increasing by 2 every time, we know it's going to be 2 times n. But if this is when n equals 1, 2 times 1 is 2, I need to add 1. Then n equals 2 works, right? 2 times 2 is 4, plus 1 is 5. Oh yeah, it seems good. Okay. And then it's alternating. So we need either a -1 to the n or a -1 to the n plus 1. And basically, you just kind of decide which one is by testing the first point. So if you plug in 1, -1 to the 1 is -1. That's what I want. I want a negative first. I don't want -1 to the 2, which is +1. Not this one, this one. So putting all these pieces together, our a sub n is going to equal -1 to the n times the fraction, 2n plus 1 on top, n squared on the bottom. Let's look at 14. One thing, oh no, actually that's not true. I was going to say something, but I don't think it's true. Yeah, never mind. I was like, I don't see any L'Hopital's rule, but there was a went to L'Hopital's rule and did limits in the first part. So 14, determine whether the sequence converges or diverges. If it converges, find the limit. So our first sequence in part A is 2 plus n cubed over 1 plus 2n cubed. So really, to determine whether or not the sequence converges, you take the limit. Take the limit as n goes to infinity of, I might rewrite this as n cubed plus 2 over 2n cubed plus 1. There's a couple ways you could do it. I do think you should show your work, meaning you shouldn't just jump and say, well, I know it's going to be 1/2 because the degree on top and the degree on the bottom are the same. So the limit is the quotient of the coefficients. I would either use L'Hopital's rule 3 times or probably actually just divide everything by n cubed. Let me simplify. If the limit as n goes to infinity, n cubed divided by n cubed is 1. You have 2 over n cubed. 2n cubed over n cubed is 2. And you have 1 over n cubed. And now as n goes to infinity, 2 divided by something that's getting very, very large is going to get very, very small. Same deal with 1 divided by something getting very, very large. It's going to get very, very small. So left with 1 plus 0 over 2 plus 0, which is 1/2. So we would say that this sequence, a sub n equals 2 plus n cubed over 1 plus 2n cubed, converges, and it converges to the value of 1/2. Let's look at part B. a sub n equals 9 to the n plus 1 over 10 to the n. So whenever you have something like this where it's something to the n over something to the n, it's in your best interest to make it so that both of them are raised to the same power, meaning like if you had like 9 to the 2n over 10 to the n, you want to write 9 to the 2n is like 9 squared to the n. Here, this plus 1 is kind of giving me a problem. So I'm going to write this as 9 to the n times 9 over 10 to the n. I'm going to break it up as, I'll put this 9 out in front, and then 9 to the n over 10 to the n, I could rewrite as 9 over 10 to the n. And now we're asking, does this converge or diverge? Well, if we take the limit, as n goes to infinity, of 9 times 9/10 to the nth power, well, if you have something raised to the nth power, if that's something, which we usually call r for ratio, if this number, if this ratio, we call r, is between -1 and 1, so that is if your r is less than 1 and bigger than -1, then r to the nth power gets really close to 0 as n goes to infinity. What's happening is you're taking this number that's less than 1 and multiplying it by itself over and over and over and over again. If you do that on a calculator, grab my calculator real quick. Yeah. So if you take, 9/10, sorry, clear. 9/10 times 9/10, it's smaller than 0.9. If you do it again, right, 9/10 is 0.9. If you keep multiplying by 0.9, oh, it gets smaller, 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 smaller. It keeps getting smaller and smaller and smaller. And that's always true. Whenever you multiply by something that is less than 1 and bigger than negative, so between -1 and 1, your overall value is going to get smaller and smaller and smaller and smaller and closer and closer and closer and closer to 0. Will it ever actually equal 0? No, but it'll get very, 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 very small the more you do it. So when you see something like this, where that number is less than 1 and bigger than -1, say, oh, great, that limit's going to be 9 times 0, which is 0. So this sequence, 9 to the n plus 1 over 10 to the n, converges, and it converges to 0. Let's look at 15. We're almost done. Except for the graphic. We'll come back and do later. So 15 says, write out the first few terms of the sequence given by a sub 1 equal to 1 and a sub n plus 1 equals 1/3 times a sub n plus 3. Now, an actual question should say to write out a specific number of terms. Let's write out 5 of them. We'll see. So a sub 1 is 1. So then if we let n equal 1, a sub 1 plus 1, aka a sub 2, is equal to 1/3 times a sub 1 plus 3. And you're going to plug in this value for a sub 1. That's how this always works. So you're going to get 1/3 plus 3. It might be in our interest to simplify this. It might not. I'm going to simplify just in case. So great, we got 10/3. Okay, let's find a sub 3. So a sub 3 is going to be 1/3 times a sub 2. Now this is how these recursive ones always work. It's just the next one is the same formula, just plugging in your new value for the previous one. So this 10/3 here gets to come down over here. So we're going to get 1/3 times 10/3 plus 3, which is going to be 10/9 plus 3 is 27/9, which is 37/9. Oh, yeah, I don't know. I don't see a pattern yet. Let's do a couple more. So a sub 4 is going to be 1/3 times 37/9 plus 3, which is going to be, all right, let's see, 37/27. And 3 is 81/27. Gross. That's going to be 118 over 27. One more. So it'd be 1/3 times 118 over 27 plus 3. That's going to be 118 over 81. And then 3 times 81 is 243 over 81, which is going to be something. 343 plus 18 is 361 over 81. Okay, so here's what I point out. 10/3 is equal to 3 plus 1/3. I know that's already over here, but okay. 37 over 9 is 4 plus 1/9. Right, because 36 over 9 is 4. 118 over 27 is 27 times 4 is 104. So this is 104 over 27 plus 14 over 27, which is 4 plus 14 over 27. So far, bigger, bigger. Let's see what this one is. 4 times 81 is 324. Just 324 over 81 plus whatever's left, which is 37. I feel like I'm doing more work than I need to be doing, but that's all right. That's 4 plus 37 over 81. Interesting. So this one got a little bit smaller. I'll just point out because 14 over 27 is a little bit bigger than a half. 37 over 81 is a little bit smaller than a half. Interesting. So then the question is, make a guess as to whether the sequence converges. My guess, I mean, really, when the question asks you to guess, you're like, well, let me just go do the work and then change my answer to whatever the right answer is. My guess is that yes, it converges. Probably to something around 4.5 because we got bigger, bigger, bigger. This is a little bit more than 4.5, and then this is less than 4.5. So the fact that we saw it get smaller here makes me think it probably is convergent. That's right. Bigger, bigger, and then smaller here. That's what makes me think we're probably on the path. Let's do the work. So the problem then says, by taking the limit as n goes to infinity of both sides, determine what the limit would have to be if it exists. So if we take the limit of both sides, limit as n goes to infinity of a sub n plus 1 equals the limit as n goes to infinity of 1/3 a sub n plus 3. So what we're going to do, this is where we do the whole thing where we replace the a sub n plus 1s with L's, because we're saying, oh, if this limit exists, it's got to be L. And if the limit of a sub n exists, it's got to be L, or whatever we're calling it. So then we multiply both sides by 3 to get rid of the denominator. So we have 3L equals L plus 9. And then we're going to get 2L equal to 9. Oh, look, I guessed it exactly right. L is 9/2 or 4.5. Cool. So if the limit exists, because we don't actually know it exists, we just know that this is what it would have to be if it existed. The limit would be that is the limit as n goes to infinity of a sub n would equal to 1. Okay, not terrible, I suppose. All right, last question. Other than the graphic, which I'm going to do later. Find the equilibria of the difference equation xt plus 1 equal to 4xt over 1 plus 5xt. Xt plus 1 equal to 4xt over 1 plus 5xt. That's not a 2, that's a t. When you're trying to find the equilibrium, you should just set everything equal to the same letter, x or whatever you like. So we're trying to solve x equal to 4x over 1 plus 5x. Same deal I did last time. Multiply both sides by your denominator. So I'm going to multiply both sides by 1 plus 5x. I think I'm showing an extra step here, but that's okay. Right. The reason we did that is so that these cancel out. So we have x plus 5x squared equals 4x. Subtract 4x over here. I feel like this is not the number I was hoping for, but okay. So we're gonna have 5x squared. X minus 4x is minus 3x. Factoring out an x, we're left with a 5x minus 3. So we get two equilibria. So one equilibrium, and let's call them x hat. We have x1 hat is going to be 0. And our other equilibrium, let's call it x2 hat, is going to be 3/5. Classify them as unstable or stable. So the way you should do this, if you're not told to do it one way or the other, and your thing is not particularly easy to graph, which y equal to 4x or 1 plus 5x is not. I know I said y, I said y on purpose, right? If I was graphing this, I'd think of it as y equal to this function. Graphing that is not super easy. So I would use the other criteria, which is that if the derivative of this, so we're going to set f of x equal to 4x over 1 plus 5x. We're going to take the derivative, and then we're going to plug in each critical point, and if the absolute value of the derivative is less than 1, it's going to be stable, and if the absolute value of the derivative is greater than 1, it's going to be unstable. All right, so derivative is going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, all of the bottom squared. You don't really need to simplify this if we're going to plug in these points, but simplifying it also isn't that bad. So I'll point out that if we simplify it, we're going to get 4 plus 20x minus 20x all over 1 plus 5x squared. And the 20x is canceled. Sorry, 5x squared on the outside. It's canceled, so your derivative is going to equal 4 over 1 plus 5x squared. Plugging in 0, and then taking the absolute value, we get the absolute value of 4 over, although you don't really need any absolute values here because everything's going to be positive, but hold on. So it's going to be 4 over 1, which is 4, which is greater than 1. So x1 hat equal to 0 is unstable. Let's do the other one. So the absolute value of f prime of 3/5. Now, everything in my heart is telling me that this one's probably going to be stable, because usually the reason you're asking a question like this is so that one of them is stable, one of them is unstable, so that you're testing whether the students know what the correct criteria is to check for. So I plug in 3/5, I'm going to get 4 divided by 1 plus 5 times 3/5 is 3 squared, all in absolute value. That's going to be 4 over 4 squared, which is 1/4, which is for sure less than 1. So great. The other equilibrium of 3/5 is stable. All right, that's all I've got for this second half of the Challenor final review, less the homework, the problem 8 graphing problems. I'll try to get those graphing problems hopefully sometime later today. I'm not exactly sure about them because the instructions are kind of weird. So yeah. All right, that's it for now.